So welcome to the International Seminars of Frontiers of Material Science. We are going to attend a presentation from Marco BACCI, Master in Engineering Mechanics, Mechanical Engineering from the University of Firenze. The topic is mainly molecular dynamics. He has 1.5 year experience in this field. He has been working after his bachelor degree and his master's degree as a PhD student with Professor Paolo Maria Mariano at the University of Firenze. And as I say, the principal research lines are basically molecular dynamics, the coarse-grained version for numerical simulations. This is the general field. But basically, the presentation will be about analysis of transport of proteins across biological nanopores. And the purpose of this work is to end up with a macroscopic, large-scale simulation and description of the behavior of the macromolecules. He has been working with the team at the University La Sapienza di Roma with respect to the molecular dynamics, and also in Los Alamos National Laboratory in the United States. And we welcome him very much because this topic is of interest for many of us. So please go ahead.
And for this kind of invitation in this stimulating scientific facility. Today I will treat mainly the transfer of biomolecules across membranes, a process that is called translocation. I wish to thank my collaborators, which are Professor Paolo Maria Mariano of University of Florence and Scuola Normale Superiore La Sapienza, Scuola Normale Superiore of Pisa, and the staff scientists of Los Alamos National Laboratories, Gnana Karan, and as well the guys that I work with in Rome, Dr. Fabio Cecconi from the National Council Research Institute, and Professor Casciolla and Dr. Mauro Chinappi from the University of Rome La Sapienza. After a brief introduction on voltage-driven translocation experiments and technology, I focus my attention on a particular experiment that involved the translocation of the maltose-binding protein for different levels of the denatural concentration in solution. Then I will tackle the modeling we use to model this process, as well as the molecule shape and its surrounding as the pore and the dynamics involved. And I will show you the main results of this analysis. These results drove us to investigate also the stretching in AFM-like stretching simulations to compare the outcome of this simulation with the results of the translocation simulations. The reason we are going to do that, it will be clear later in this presentation. And then finally, I will tackle a preliminary continuum model that tries to enrich the standard continuum approach by selecting a morphological descriptor for the protein to follow the evolution of the molecule. The evolution of the morphological descriptor is, in turn, controlled by a balance of interaction over the protein itself. Since the first experiment of translocation was performed by Kasjanovic and co-workers, up to current experiments, the basic experimental apparatus has always been like a microfluidic cell with two chambers connected by a pipe, and an applied voltage generates an ion current that provokes the passage of the molecule through the sensing area of the device, which is actually a nanopore that can be both biological, solid state, but mainly biological till up to date. And of course, when the molecule passes through the nanopore, it provokes a drop in the ion current that can be recorded with standard electrophysiological techniques. And this is what is called a direct measure of the transport time, of the translocation times. So we are able to measure directly how long does it take the molecule to pass through the pore. Here you see probably what the most famous biological nanopore used in this kind of experiments. It's the alpha-hemolysin, that is a protein toxin which is able to migrate and spontaneously insert into lipid V layers to form the sensing area of the device, or what are called single nanopore systems. Of course, you can have also multi-nanopore system to do statistical analysis, but to sense single protein, single nanopore system with just one sensing area are mainly used. Very recently also solid-state nanopores have been developed, but the experimental applications are still seldom. Up to date, many efforts have been done to obtain with these devices what I can call fast DNA sequencing. The main idea behind this approach is to be able to sequence the DNA, like distinguish the different ion current drops that characterize each base of the DNA. That means any oligonucleotide of the DNA has a characteristic ion current drop, and ideally one is able to distinguish in between the different bases, and so it is able actually in principle to sequence the DNA. This approach has some drawbacks, mainly random fluctuation due to thermal fluctuation into the variability in the number of particles that are passing through the throat area of the nanopore, and due to the high velocity of the passage. So it's kind of easy to guess how molecular dynamics are a good tool to go along with experiments to achieve the target of fast sequencing. Translocation of protein has been less studied than DNA, and from, let's say, a sequencing point of view, it's a process much more complicated, because the DNA is composed of 5 elementary molecules, 5 different oligonucleotides that you have to be able to distinguish. Here, proteins are actually made of 20 different types of elementary molecules, the amino acids. So the ability to be able to distinguish between different elementary molecules has to be greater in the case of protein. One of the latest successful attempts was made by Telaga and co-workers a few years ago, where they were able to distinguish different molecules, the passing of different molecules in solution, modeling the ion current drop with a simple ohmic term, a resistive ohmic term, multiplied by a corrective factor that takes into account the geometrical shape of the molecule. And this line of reasoning will probably be enhanced in future, taking into account other physical and chemical aspects to obtain, to achieve the target actually of sequencing of protein. I focus now on an experiment on translocation of a particular protein called maltose binding protein, performed by Eucalid and co-workers. They studied the passage of this maltose binding protein through the nanopore, the alpha-hemolysin nanopore, for different level of the denaturing concentration in solution. They observed, among other things, that for low level of the denaturing concentration in solution, that is here and here, they observed no passage, no translocation. So actually, at least for the force field, they were able to reproduce without destroying the lipid bilayers. The alpha-hemolysin didn't go through, because it's too big, didn't go through the alpha-hemolysis. While increasing the denaturing concentration, they pass from this situation to a situation where current ion drops are like a lot, and their frequencies actually increases with the increase of the denaturing concentration, and the duration is shortened in time. Here you see, for example, that for low level of the denaturing concentration, you have both short events where the molecule translocates fast, and you have kind of long events where probably the molecule gets stuck in the pore due to partially folded, partially still closed region along its structure. We try to model actually these experiments by modeling the protein, the denaturation of the molecule, and we try also to reproduce. We concentrate our attention in this area to find out the reason for long blockages. Rapidly, the maltose binding protein is a globular monomeric protein composed of two main subdomains, the C and N lobes, which closes to form the binding site. It has been widely studied from an experimental point of view. Ganesh and co-workers studied its unfolding pathways, both from a thermal and chemical point of view. It means that when you put the molecule close in solution, you can make it open, increasing the temperature or using a chemical denaturant, and they found out that actually the unfolding pathway is a simple two-state pathway, so or the molecule or is closed or is unfolded like single file in solution. Very recently, Birch and Reef studied the mechanical properties of this molecule by pulling this molecule from its end in AFM experiments, and they found out that actually from a mechanical stability point of view, it is composed of four main elementary blocks, groups, called unfoldons, that they call unfoldons, which detach sequentially. I mean, if you pull this protein, it doesn't open mechanically in just one step, but we will see it follows like a sawtooth with peaks, because these subdomains, they open sequentially. First is the M1 unfoldon, followed by the couplet unfoldon, these two, and then finally is the yellow one that unfolds, that detaches. Very recently, Pastoriza and Lego studied the translocation of the maltose binding protein through another biological pore, the alpha-rhodizine. So here we have the native structure of the protein from the protein data bank. And so we modeled this protein through a coarse-grained approach, passing though from a situation like this one to a set of material points in space which coincide with the C-alpha carbon atom of the main backbone chain of the protein. According to the Go model, we set some interaction potentials among these material points. Here you see how we model the peptide bond by an harmonic potential, and then we have an attractive potential on the bending angle and on the torsional angle. Of course, the ground state of this system is the native structure of the protein that you have just seen. The Go model, to be able to reproduce the native state of the protein, needs the assignment of some long-range attractive Lennard-Jones interaction that bonds amino acids which are not like very close to each other in the sequence of the chain, but they are close geometrically in the native structure of the chain. The parameter that controls how many of these attractive Lennard-Jones interactions are formed is this one, the cutoff radius, which is the main parameter that we use to model chemical denaturation. So as you see in this sketch, these amino acids, K and J, are thought to be, their distance with respect to amino acid I is thought to be lower than the assigned value of the parameter cutoff radius. So they will interact attractively in our model. More specifically, this is the real structure of the protein. These two amino acids that I highlighted here, they are not in sequence in the chain, but they are very close to each other. So they will probably interact attractively for very low values of the cutoff radius RC. Instead, for all the other amino acids that are not bonded in the ways I just described, we assign a repulsive interaction, like here between amino acid I and M, to take into account the excluded volume effects. Other potential that enters our simulation are axis-symmetric soft co-repulsive potential that models the pore. The importing force is constant and always applied to the last residue present in the pore, and the dynamics selected for the process follows a Langevin equation. That it means that we are performing our simulations at constant temperature. Before performing translocation simulations, that is, before pulling the protein through the pore, we study chemical denaturation of the molecule. And here in this phase diagram, you see how much a given structure resembles the native one. In the dark region, you have structures whose root mean square deviation from the native structure is low. So in this area, you have folded structure that resemble the native crystallized structure of the protein. In the bright region, instead, the protein is unfolded. And you see how by varying the value of the cutoff radius, we are able to pass from folded structure to unfolded structure at constant temperature. And this means that actually the cutoff radius, it means to us that the cutoff radius is able to control, to model chemical denaturation. We also obtain that data collapse that map the value of our parameter, the cutoff radius RC, with the parameter that controls denaturation in real experiments, that is the denaturant concentration in solution. And here you see the data collapse of our cutoff radius on the concentration of the denaturant in the two-state unfolding pathway by chemical denaturation by Ganesh and co-workers. And you see that actually in between 6.8 and 7.5 Armstrong, for us the molecule is folded at the working temperature, while in between 6.2 and lower values the molecule is unfolded. So here in this little range of the cutoff radius, you have the transition from folded to unfolded state. Here just an example to let you follow me in what we do. We actually have this protein and we pull it through the pore and we study what happens. We have we can find out different quantities like translocation probability, as we will see, average time of translocation. Here in this example, the pulling force is high and the molecule fully translocates. But this is not the only outcome you can have from simulations. If, for example, the pulling force is not high enough, it can happen that you have the molecule that leaves the pore mouth, it doesn't go through, and we call these events as lost events, while in other cases, at the end of the simulation, of the allotted time for the simulations, you find that the molecule is nor lost, neither completely translocated. Actually, it is remaining stuck in the pore at the end of the simulation, and we call these events as unsuccessful. Here are some outcomes of our simulations. We define the translocation probability as a function of the pulling force, as the number of successful simulations, where successful means completely translocated, over the total number of attempts, both for C-terminus pulling and N-terminus pulling, which are N-terminus and C-terminus are the ends of the molecule. So you see that the trend of the translocation probability is a step-like trend, and this probably involves the overcoming of a free energy barrier. These data are relevant to a cutoff radius value of 6.8 Armstrong. It means that these values refers to a configuration of the protein that is folded. When it's pulled through the pore, it's closed. Here you see the probability that the molecule gets lost in the bulk sharply decreases, increasing the value of the pulling force, while the probability it remains stuck at the end of the simulation in the pore shows a peak for the average value of the forces. And you also see how pulling from one end of the molecule from the other is not the same. So this process is kind of not symmetric. If you pull from one end or the other, the outcome is different. And we also define the critical force as that value of the force for which translocation probability is equal to 50%. So you have 50% of the molecule translocated and 50% or lost or like stuck in the pore. Plotting the value of the FC, the critical force, as a function of the cutoff radius, you see how you are able to distinguish between folded and unfolded structures, like you are able to do that varying when it is possible, like with solid-state nanopores, the value of the voltage that drives the translocation. So you see actually that this parameter does not change. The value of the pulling of the critical force does not change for unfolded structure in this range of the cutoff radius. Practically, the critical force is constant because the translocation is dominated by thermal fluctuation. You have to overcome only thermal fluctuation to let the molecule pass by. Instead, when you start to have folded structure here in this range of the cutoff radius, you have an increase in the value of the critical force, that also has to do with the increasing in the free energy barrier that you have to overcome, because here, like the internal energy of the protein due to the bonds long-range interaction increases, and it makes the translocation process more difficult. Also, the complementary probability of translocation events are mainly lost events for unfolded structure, and mainly unsuccessful or stuck, if you want, events for folded structures. So here we have two parameters that actually are able to distinguish between folded and unfolded structures. Here I plot the trend. Here you see these points are the value of the average translocation time as a function of the pulling force. Here, this dotted line is like the approximation due to this formula. As you see, every unfolded structure actually collapses on the same curve. So they have the same collective behavior. It means that you cannot distinguish by the average translocation time the value of the cutoff radius for unfolded structure. And this curve is modeled by two functions. The first one is an Arrhenius-like term, an activation term that models the fact that you had to overcome thermal fluctuation, and it rules mainly in the low region of the pulling force, while in the region of high forces, translocation is dominated by this, I would call it ballistic term, but actually it's a constant velocity term. So if the force is high enough, translocation proceeds at constant velocity, and you don't feel any hindrance due to the molecule structure. The picture of for folded structure, that is for higher values, increasing value of the cutoff radius, is instead more rich, as the average translocation time depends on the value of the cutoff radius, and if the course increases if you increase the value of the cutoff radius. The collective behavior is obviously recovered in the high range of the forces, as all these data collapse on the same curve. Because it's true, if the force is high enough, you don't see any hindrance by the structure, also for folded structure. Here you see a time distribution of typical translocation processes for unfolded structure that can be fitted easily by an inverse Gaussian, which is the time distribution of a biased random walk, and it's very peaked on the average value, while here you have the time distribution of the translocation for a folded structure, and you see it has fat tails, and this suggests us that here the phenomenology of the transport has to be much more rich. There should be some explanation for these long tails to happen. And we are going what's going on for the structure. These are two examples in panel A and panel B of like typical translocation pathways for folded structures, pulling from one end and from the other, but it's practically the same for what I want to say. Here you have the number of residues still present on the cis side of the pore, that is the left side of the pore, the starting side of the pore. And you see that the molecule spends most of the time in particular configuration, most of the times of the simulation in particular configuration corresponding to this plateau. Actually, you see along this plateau, the simulation is running, but the protein is stuck in a configuration then can be detected, can be selected by the number of residues still present at the pore mouth. And this is both the same, these points are different, of course, but it happens for C-terminus pooling and N-terminus pooling. Also averaging over all translocated simulations, which is kind of 500 simulations, you see that the molecule spends most of the time of simulation around this particular configuration. It spends most of the time of the simulation here and here in these peaks for N-terminus pooling, and in these three peaks for C-terminus pooling. So actually there exist critical areas of the protein structure that when they face the pore entrance, they hinder the translocation. Or rather, if the protein gets stuck, it will do it only when these critical areas, from the mechanical stability point of view, are facing the pore entrance. In panel E, instead, you see how the translocation process is mainly smoothed, is much more peakless and uniform for random coil, for an unfolded structure. So we wondered if what's the physical reason involved in these critical areas, and if unfoldons, the domains, the elementary domains we saw previously, have a role, if they do rule, also in translocation pathways or not. So the first thing to do to answer this question, I remind you briefly what's an unfoldon. These are elementary blocks of the molecule that you see in the experiment by Gertz and Reef. They detach sequentially. So if you put this one, if you put the molecule, first is the blue one that opens, followed by the couplet opening of unfoldon M2 and M3, the green and the red one here. They are their unfolding pathway is couplet. And then finally is the yellow one, unfoldon M4, that detaches. So the first thing to know, if does unfoldon exist in our model, is the Go model able to reproduce unfoldon? So we perform some stretching simulation, actually keeping one end constant and pulling the other end at constant velocity or constant force, to see if unfoldons actually exist in our Go model. And then here you see a qualitative series of peaks. Let's see how the protein unfolds. Actually, where of course you have the color code for the unfoldons. Actually, it's really unfoldon M1 that opened for first, and then you have the coupled unfoldons of M2 and M3, the red one and the green one, and then finally is unfoldon M4 that detaches. So also from a qualitative point of view, we are able to reproduce the picture we just saw for this experimental picture. This is not only qualitative, but it's also quantitative. As you see here, we are able to reproduce the so-fit landscape of the translocation. Here you have the force of the pulling, and here you have the end-to-end distance, the distance between the two ends of the molecule. So you see, actually, and here you have a parameter that tells us how much an unfoldon is opening, is stretched, is detached. So here you see that the first peak actually corresponds to the detachment of unfoldon M1, the blue one. Then the second peak corresponds to the actually coupled unfolding of M2 and M3, as here in this region from here to here. Mainly M2 and M3 are unfolding, and then finally we have the detachment of unfoldon M4. So actually unfoldons are well reproduced by our coarse-grained approach. Let's see. Here you have just to brief a video where unfoldons are highlighted, and you can already guess that there is not, except this case, the last case, I skipped the other video for time, that there is just a little coupling between unfoldons, the boundaries of unfoldons, and the critical regions that we find in translocation. This is more clear from this picture. Here you see highlighted in black lines the critical areas stemming from translocation simulation as a function of the number of residues on the cis side, and you see the evolution of the unfoldons in translocation experiments, in translocation simulations. You see that only in this case, only for this line, actually this structure, this critical area coincides with the boundary of unfoldon M3 that is just detached here, and unfoldon M4. So this is only 1 on 5, and so we deem that actually translocation pathway is really different for translocation when you have the pore than from AFM stretching line simulation. So actually we don't feel that we can answer why do stalls exist. The answer is not the presence of unfolding, it has to be something else. And the answer is actually stems out from counting how many long-range attractive Lennard-Jones interaction a given little structure over the protein does with the rest of the protein. This is a contact map. This point shows you, given an amino acid like this, how many contacts and with who this amino acid is linked. attractive Lennard-Jones long-range interaction. So here you have the density of contacts. This peaks means that this region of the protein, like here, this little region of the protein, is forming, as this peak is high, a lot of native contacts. It means that it's bonded a lot with the rest of the structure of the protein, with distal regions. And here in gray are highlighted the critical areas stemming from translocation simulation. So you see that there is a very good correspondence between these critical areas and these peaks. Only this one is actually not felt because we go too fast. This is I saw this for the low values of the force. You can see also this peak. So actually, also just from a static analysis, you are able to guess which are the, let's say, possible areas, critical areas of the translocation, just from a contact map like this. So the physical explanation is simple. Actually, when a critical area is facing the pore mouth, it's carrying with itself a lot of other structure of the protein to which it is bonded. Like this one is bonded with these two big regions behind it. And so to let it pass through, you have an hindrance due to the approaching of distal region of the protein, and then you have to break a lot of bonds, of long-range bonds. And this is the explanation of the blockades. Here you see the density of blockades in the critical areas, this one highlighted in blue for the C-terminus pooling, for the N-terminus pooling, and in red for the N-terminus pooling. You see that the density of contact is much higher in this region than in the complementary ones. So this is our explanation for the blockades. And this is actually the end of the real molecular dynamics stuff. And I come now to the standard one-dimensional continuum modeling of such processes. It is customary to consider in literature to summarize the process in order parameters that are called reaction coordinate. And you can imagine you have a reaction coordinate like the coordinate along the pore axis of the point of application of the force, or for example, the center of mass of the molecule. These order parameters are thought to undergo a Langevin dynamics that in a Langevin dynamics in a proper free energy profile. This is the free energy profile. And in the overdamped limit, so where you can neglect the acceleration, and for constant diffusion coefficient, this equation is equivalent to a Smoluchowski equation for the probability P to find the reaction coordinate, for example, the center of mass of the molecule, at point x in time t. So such a framework can be solved with proper boundary conditions like radiation boundary conditions to obtain closed form solution for first passage time statistics like translocation probability and average translocation average time to compare the results of simulation or experiments with. So actually this approach, here you see a typical free energy profile as a function of the reaction coordinate x along the protein, along the pore, which has a trapezoidal shape. So this approach is actually already a flexible tool to interpret results beyond just mere fitting. But you see here, you have just a one-dimensional object, actually a one-dimensional order parameter that summarizes your process. And we are trying, preliminary I have to say, to enrich this picture by selecting a second rank tensor that can be considered a collective parameter, an order parameter, to give gross shape, a gross evolution of the protein shape. So we want to have something that tells us how the molecule is deforming attached, let's say, to its center of mass in dynamics like the EFM stretching, the thermalization, the translocation. So we select according to the literature on like kinetic of molecules, a second order parameter, a second rank tensor μ, who has the role to describe the evolution of the protein shape. So this order parameter
is actually a morphological descriptor for the protein. So in light of the mechanics of complex material, interactions are power conjugated to its rate, and can be balanced by requiring some power invariance with respect to changes in observers. So what I want to point out here is that the protein is actually, in this point of view, in this approach, is seen as a single material point, a single material element with inner structural material element. Like it can be thought to be like the material element of a coarse grain of a granular body, as a protein is composed of interactive beads, and it clearly reminds to a granular body. So from the fulfillment of the second principle of thermodynamics, actually, let me say that in this approach, this material element is isolated because we have just one protein. So if it is isolated, you don't have any contact interaction, there is no microstress. So only a self-interaction arises, whose dissipative part, to fulfill the second principle of thermodynamics, has to be equal to the rate of our morphological descriptor. So actually here we have our easy, very simple elementary evolution equation for our morphological descriptor. The assessment, the definition of the inner self-action ZA arise from equalization of the power of the forces inside the molecule, the real molecule, let's say the molecular dynamics molecule, with the power associated with the self-action in the coarse-grained representation of Ni, and it is treated in length in these references. What stems out is a definition for the self-action as actually divided by the volume of the element, volume of the material element, and here you have a tensorial product between the forces, the atomic forces exerted between residues I and J, times the point of application of these forces with respect to the central mass of the central granule, with respect to the central mass of the protein. So this is our definition of the self-action, and this is the definition of our evolution equation for our morphological descriptor. With these ingredients, I'm able to compute how the morphological descriptor evolves in different simulations. So after some preliminary simulation to set some constant parameter, the value from some parameter, I studied the evolution of the symmetric part of the morphological descriptor that I obtained by polar decomposition. Actually, what I have to say is that in the general approach, both forces and the point of application of these forces are time dependent. So if you take an harmonic oscillator made of just two beats, two material points, and you keep forces and distances as function of time, you have to integrate something that actually is a square sine or a square cosine, and so it diverges in time. Also, the previous model for the self-action gives you entries of the morphological descriptor that, if you integrate in times, they diverge. And it's actually what we see here. This is a thermalization simulation, I guess. And here you see the evolution of the gyration radius, which actually what we want to reproduce. And here you see the evolution of the first eigenvalue of the symmetric matrix associated to the morphological descriptor and stemming from polar decomposition. And the other two evolutions of the other eigenvalues are the same, so actually this is monotonic and does not describe in any way the evolution of the shape of the protein. So the first approach, the first thing I did to overcome this problem is to keep distances constant to the value that I can guess, or from the crystallized structure, or from the initial structure, the thermalized one that I use for every simulation. Actually, the second approach works much better, and I keep the forces varying. This approach works well if the dynamics is in a sense constrained, as in thermalization, as in AFM like stretching simulation or translocation, where you have something that constrains the molecule to have let's say a regular behavior. Here you see the evolution of the volume of the ellipsoid, this red curve, with respect to the gyration radius to the power of 3, which is a measure of the volume of the molecule, of course, and you see a really good compliance in between these two quantities. And here you see how actually it evolves. Here you have the ellipsoid stemming from polar decomposition, and it is attached to the central mass for graphical reasons, and it elongates following kind of well the evolution of the protein shape. And also I was able to take into account rotation pairs that are mainly due to this coordinate system of eigenvectors by diagonalization of the symmetric part, rather than by the rotation matrix of polar decomposition. Unfortunately, when you go to non-constraint dynamics as a thermalization one, this model does not work anymore, and I had to figure out why. Here you see practically the same trend of the volume of ellipsoid for two different molecules. One, the green one, is supposed in a thermal bath. The green one, the molecule associated with this green evolution, is thought to be folded in this thermal bath, so it doesn't open. While the other one, it unfolds, it opens. As you see that the evolution of the volume ellipsoid is practically the same, so we are not able to distinguish between a molecule that if put in a thermal bath, it opens, and a molecule that if put in the same thermal bath, it remains closed. So to overcome this drawback, I had to change a little bit the definition of the self-action, and I took the force constant, like not constant, like the absolute values of the entries of the force, and I considered the velocity of the point of application with respect of this force, with respect to the central mass of the protein. And I added a constant that actually puts more weight on the inner distances than on the forces. With this approach, with this new definition, I'm really able to follow almost point by point, and not even in an average sense, the evolution of the radius of the duration. Here the purple and the green one, the green one is the radius of the duration of the molecule that put in the thermal bed unfolds, and this is the purple one, is the evolution of the volume of the associated ellipsoid. And you see that actually they resemble each other very well. And here you have instead what happens for the molecule that put in the same thermal bath does not unfold. It means its duration radius is practically constant, and the volume of the associated ellipsoid is practically constant and much lower than the volume of the ellipsoid associated with the molecule that unfolds. And here it just, you see what I was talking about. You see that this ellipsoid associated to the molecule that is opening has actually a detectable evolution, while this other one practically does not change its shape. I am able to follow the rotation here, but they do not add anything because they are they just over the evolution, so I didn't consider it here. So this is the point I am. Here I can summarize all the steps I took in my PhD research, but I'm not going through this. So in the near future, what I hope is to be able to find out the free energy profile by standard techniques like umbrella sampling simulations and multiple weighted histogram methods, and maybe to find a way to compute the evolution, the free energy trend following the continuum approach, as you have some equation that links your self-interaction with the profile of the free energy, but this is really preliminary. So I thank you for your attention. I concluded. Gracias.
Okay, it's time for a few questions from the audience.
Well, I have first to apologize because I'm not an expert on this topic. However, when you were talking about the discrete, all the molecules in interaction, I wonder how you take into account the molecules which are close to the one for which you are finding the interaction. I suppose that if you have a very small number of molecules interacting, that would be easier, but as far as you are getting more complex molecules, you will have, and especially if you are stretching the structure, perhaps it would be a little bit difficult to keep track of that. Is there any trick about the, because it is a problem we find also in SPA simulations. I mean, when you take into account granularity, you have to search for neighbors. So
Yeah, that's true.
the question is, what is the trick you are using? Because we are very much in that.
Well, the trick is very, no problem. I wish I could answer it. But the trick is here that is just that I have one molecule by time. I don't have more than one. So I'm studying really a single molecule undergoing single thermalization or unfolding or stretching. So actually, here my material element coincides with one molecule. I don't have many molecules in my approach. I just one. So I don't have any bonding interaction between different molecules. As I think this Go model, the coarse-grained approach I'm following, is not suited to have more than one molecule, because actually, as far as I know, in the literature, I never saw a way to let like different molecule interacts with coarse-grained description. I think that I would, if I had to do that, like right now, I would just simply assign what I show, like excluded volume repulsive Lennard-Jones interactions in between the amino acids of the protein, but that's just what the first thing that comes into my mind right now that I'm talking. I really don't know if it will like be suited for this approach. But I think so, it could work. Why not? I think that the first thing I would do to enhance my model and consider more than one protein, like undergoing thermalization, for example, in the same thermal butter, I put more molecule. The first thing that comes to my mind is the crash of
because they are evolving and then you have to.
Yeah, if I want them to be separated, then I apply repulsive interaction, Lennard-Jones interaction between the two molecules. But I mean, you probably need also to study how the molecules are really in the physics, because they could actually attract each other, some parts of them. Probably an SIG model in that case would be more appropriate, because it takes into account a little bit of the chemistry involved in the single residues. But I had no experience about that, not yet.
Thanks.
I go first. A quick question. You were talking about probability of being stuck on one side with respect to the other one. Obviously, I mean, it's not a very complex molecule, but I guess we're talking about nanosecond simulations, or maybe microsecond.
Nanoseconds with coarse-grained, yeah.
And how does it, because in this case, your probability is changing with the time you're looking at. So how does it compare to experiment? I mean, are you sure that your timing is enough to be able to compare something to the experimental setup that you presented at the beginning?
Let me see. When you use like a coarse-grained approach as the one I use, the unity of measures is like what are usually called cold unity of measures. So if you keep, for example, as we did, a perfect correspondence in length, then you lose it in time. So we have angstrom, but we cannot like easily map our time with the time, the real time, the experiment time. So our results can be compared from a phenomenological point of view with the results of experiments, but not really from a quantitative point of view. It means I'm not really able to map. You saw the plateau previously, and it has a duration in time in my simulation, but I'm not able to map it with the blockages that you saw in the experiments. Like I'm not able to map the time because the scales are different. To do that, it's possible, but I didn't do so. I don't know if the scales of time actually match each other. I only know that the qualitative picture is similar.
So the quantitative data about the probabilities right now is not comparable to an experimental set?
They are comparable like in trend, like in the trend, but not quantitatively.
My first question was the same. It was about the strain rates that you are applying in your MD experiments, but you have already answered. So, and the second question is in your coarse-grained model, where of course you don't have the individual atoms, but you have these blocks, and you impose like some empirical potential that you have explained, how do you obtain the characteristics, the different terms of the potential? How, because I mean, if it's a metal and you have a whatever.
Yeah, it's true. Here, you have some parameter like epsilon.
Mm-hmm.
This is the energy scale, and this is another way to like it can dampen or enhance all the interactions, because actually it's a constant that multiplies the value of your potentials, all of them. So what we do usually here, and this is customary in literature, you have this parameter equal to 1. That's why it also like don't let you compare the unit of measure using the code directly with the unit of measure of physical reality, because you are changing the scale according to this parameter that you don't know how to put, so you put 1. Well, you can change it, but usually we always put 1. Other parameters involved here, these are just distances. So this is the distance of the crystallized structure between amino acid I and J, and the actual distance in between the same amino acids. Here you have, let's say, a core, the excluded volume core. So this is a passive potential with core sigma, and sigma you take it from crystallographic analysis of the average, let's say the average dimensional amino acid of the protein, and in this case is thought to be 4.5 angstrom. The strength of molecular coarse-grained and molecular dynamics are mainly a couple that they allows you to obtain time scales when you do the transformation to the physical one, because you can do it, just maybe they didn't yet. To have transport times, stimulation times comparable with the real ones, the biological ones. While if you do full atoms, you will never be able to like simulate for 1 microsecond.
Yeah,
You are 3 orders of magnitude short.
That's clear, and I agree. But have you tried maybe to obtain those terms from full scale NV simulations of very short pieces? Yeah. Then you have the right answer.
Yeah,
you know the exact potential between those species, and then
yeah.
you try to somehow scale up to this coarse-grained model.
Yeah, it's an approach. When I was in Los Alamos, I was interacting with another scientist that was actually doing, she was doing full atoms, and she was building up coarse-grained based on the results she had on the full atoms, and then doing the step, for the next step from coarse-grained to try to continue. So yes, many times you rely on full atom simulation to set some parameters. The Go model is actually really simple, so you don't have so many parameters. These are all taken from literature. I mean, you take your molecule, you put it into the thermal bath, and you see when it unfolds, and so you decide that this is my unfolding temperature, and so you have it set, and so you can set everything else by simply thermalization.
Any other question? If not, then we thank again